a t-shirt to you, Simplify t-shirt.
And without further ado, we'll get going. So my name's Chuck. I'm joined here by Nathan this morning. We are doing the Simplify Elite IQ Installer training known as Battery Chemistry 101. So it's a little bit battery chemistry, it's a little bit battery 101. This is a NABCEP accredited training, so you can get CE credits for it. To get your CE credits, you do have to stay in for the entire training. And at the end of the training, we'll present an email address where you'll email us and say, hey, I want my NABCEP CE credits, and this is how I want my name listed. We'll go over that again at the end. And once again, let's discuss, as we've got a couple more attendees, we are having people enter the highest forecast temperature for their area into the Q&A, which I see a bunch of entries being entered. And the winner will get some swag, some Simplify stuff. We'll reach out and send something out.
Looks like Justin's temperature for today is going to be a high of 70. It's looking pretty high.
That's warmer than it is here, that's for sure. So here we go. Company history and overview of Simplify. We started in 2010 under the name of Optimized Energy Storage and Liberty Pack. These were some lithium iron phosphate batteries that hit the market in the film and broadcast industry. So they were using technology that hadn't really been used in that role before to do some cool things. Like, I don't know if you saw the newer version of Tron where they had the light up suits. Those suits were powered by our battery technology. In 2011, 2012, there was an interest in the military to have some solutions for lead acid and generator combination products that were having problems on the front lines. Lithium-ion had a bad name because of some thermal runaway events, but they were able to use our technology after some careful vetting in some forward operating bases. 2013 to 14, we started to change the product line a little bit, put in some power banks on wheels, expanding the offering. 2015-16, we relaunched as Simplify Power, the brand that you're familiar with today. And in 2017 and 2020, we were ramping up production. We started to do some high voltage products, continuing to expand our product line, with the most recent news coming that Briggs & Stratton acquisition by Simplify in 2021 led us to release a new vertically integrated energy storage system. This is an inverter, this is a battery, this is a monitoring system, all in one. We'll go over some details later in the slides, but we're really excited about using Briggs & Stratton's history of manufacturing to leverage a new product line for us. What is Simplify all about? Well, 3 basic concepts: safe, proven, and simple. It's part of the name. When we talk about safety, we're talking about our chemistry primarily, which is the topic of this talk today. So non-toxic, non-hazardous. This is because we are a cobalt-free chemistry that we can tout that. We also don't have a risk of thermal runaway with fire propagation for the same reason. A lot of cobalt batteries do have that problem, and we'll go into some details about what that looks like. Because of our safety record, we are UL certified for 1642, 1973, and 9540 via a 9540A test result. Our product is also able to get some UN DOT certifications for air transport. Not all of our products are eligible for that, so be sure you double check. But because our chemistry is safe, we can put it on airplanes. We also have SCHIP approval for the California rebate program. And we're proven with over a decade of experience. We are one of the few companies out there that has batteries in the field that are outliving their warranty life. We get calls about Liberty Pack and OES batteries that are still out there performing. And people just want to check and say, okay, what should my voltage range be? You know, well, how do I charge this? Is there a BMS? The product is still working. They just don't know what to do with it because it's 10 years old. We're deployed in more than 45 countries, over 250 megawatt hours installed. So it's very proven chemistry and product out there. Like I said, we got tested and validated by the US Army and Marine Corps, which is no small task. And we also try to prove through our business model that we can affect change and social impact and profitability can coexist. So we've got a program called the IDEA program, where we'll donate 1% of our profit towards like a grant process where worthy applications can submit their idea. Maybe it's for a school or a park or another, energy solution that needs to be deployed in the world, and we can help meet those needs in the form of donating batteries. We're also manufactured in the US, so nothing to hide behind there. And simple, like I said, it's in the name. You can use our product with just about any generation source: grid, solar generator, off-grid, on-grid. You can use it with a bunch of different manufacturers' equipment that's already out there, including existing off-grid inverters and a lot of the new products that are coming out. Why do we do this? Well, there's a number of reasons. We'll go over those in a slide here in a second, but we're backing up power. That's obviously a huge concern for people, to increase their resiliency and energy security. But we can also save money with cost savings on utility bills. We'll take a peek at that. We talked a little bit about safety. We have an entire hour-long presentation on our UL listings next week to talk on the 9540A test protocol and the certifications that result from that. So what is all that? Real quick. UL is Underwriters Laboratory. It's a third party that tests products for safety and then certifies them and gives you the ability to mark your product as UL certified. This is an important certification for batteries around fire, disaster, and safety. So 1642 is the cell. It's about the size of a AA battery, a little bit bigger. 1973 is the battery itself, so a battery enclosure that's made up of a bunch of cells. And then 9540 is the system level test. So this will typically be a battery in an enclosure, maybe a battery with an inverter. 9540A is how we get to 9540. 9540A is actually a test protocol. It's not a certification. There's a fair amount of confusion out there in our AHJs and inspection and building permitting agencies that they want to see a 95A certificate. Well, that's not a thing. 9540A is a test. It's a very long test. We publish ours. It's 70 pages long. Only a couple of redactions in there. And the reason we publish is because we're so proud of our results. And those results inform how our 9540 certification looks. Spoiler alert, we did really well. We did not have the need for auxiliary equipment or fire suppression systems or a lot of the things that other batteries are going to require to have, deflagration radiuses and so forth, to get that 9540 certificate. So why do you care? Well, UL certifications are necessary for a lot of things. Absolutely. If you're getting a system inspected and permitted for your building department, they're going to want to see UL certifications. Some AHJs may interpret them differently. Some may be more strict, some more lenient. So you're really going to want to double check with your AHJ about what they're looking for so you can get ahead of it. And in general, it's always recommended to have UL listed products. UL listings are a safety listing. So if you're going to bring something into your house or your business and you don't want your house or business to burn down, right? You want it to be a safe product. And by having that UL listing on there, you know that a third party is taking the time to verify that product doesn't pose an unsafe, fire risk. You might also need to have a UL listing for insurance policies. In the world of wildfires and homeowners insurance and all this, insurance companies are looking at everything a little bit more closely, and they may require seeing that UL listing just to get insurance. And you may say, well, Chuck, I'm not getting a permit. I'm off grid. I don't need insurance. Well, what if you decide to sell your property? Having that UL listing may make things go smoother if there's no question that the property you're selling is safe. So energy solutions are a solution to problems. We got a bunch of them. I don't think it's any mystery to anyone on the call today that energy costs are escalating. We're seeing higher costs at the gas pump last year. We're seeing higher costs for natural gas, propane. And this isn't a US problem. This is a worldwide problem. Fossil fuels are increasing in price. There's unrest in the world that are driving some of these pricing issues. And we're going to continue to see energy costs escalate. Well, what does this mean for energy solutions? Well, distributed energy resources can take some of those costs and put them in control, where if you're not paying to, say, run a generator to power an off-grid house, but you're powering it by solar and battery, you are not affected by those cost increases as much as you might be if you were only relying on fossil fuel energy source. And for those of us that aren't off-grid, there's legitimately failing infrastructure. We are seeing utilities have problems that they did not get ahead of. You know, the infrastructure is aging. We're starting to see in California, the utility will actually turn off the power in a dry weather, high wind event. They'll just say, nope, we don't want our lines energized because it's too risky. They've literally killed too many people by starting fires with their utility lines. So they'll just turn the power off. It's cheaper, it's safer than fixing the problem. But that's not the only problem. We also see the grid, being overloaded. There was a recent event in Texas, again, where, these cold weather events move in. The utility cannot provide the demand that is needed by their customer base, and their system goes offline. It's wild. So failing infrastructure is a huge motivator for customers to say, hey, I want to take distributed energy resources, which are, your solar, your wind, your battery, and take those into my own hands, put them on my own property, power my own loads, instead of relying on this utility that's becoming more and more unreliable. And then decarbonization it's a bit of a hot topic still, but I know myself and a lot of people that I've worked with in the industry are very passionate about the fact that renewable energy sources do have the potential to save our planet. If carbonization is leading to global warming and that could lead to other problems, and we have a solution, we are excited. We are empowered to actively seek that solution by putting solar on our rooftops, by getting batteries at our homes to reduce the strain on the grid during weather events or otherwise. So a lot of good solutions to the problems that we face are available through distributed energy resources. Well, how do we save money, right? There's a couple different ways to approach this. When you're connected to the grid, your utility bill will have what's known as rate signals, or ways they charge you money. So one rate signal may be a demand charge, where a utility may say that your entire monthly billing dollar amount is based on a kilowatt value that is the highest instantaneous value you draw from the grid. So it could be, in this picture on the left here, we've got a very high peak just after 5 o'clock. That's probably somebody, maybe getting home from work, turning on lights, turning on the air conditioner, turning on the oven, a whole bunch of loads stacking on top of each other and driving that highest instantaneous value that's therefore driving their bill. And that can get really costly. So one way to attack these costs is to use demand management or peak shaving, where you say, hey, I've got batteries, charging them from solar or from the grid, and I'm going to tell my inverter to discharge my batteries before I hit that highest peak. So in this instance, we've got a dotted line here, and we're telling the inverter not to go above that into the purple, therefore preventing that highest charge from occurring. So it's a great way if you're in a demand rate schedule to help curb some of the costs the utilities are throwing at you. Now, you might see demand, and you might also see time of use rates, very common in a commercial rate schedule. Well, time of use rates are going to say, hey, utilities figured out that at the afternoon and into the evening is the most expensive time to produce power. That's coming from all of their plants, hydro, nuclear, peaker plants burning fossil fuels. Because the same phenomenon is happening as the graph on the left. Everybody gets home around the same hour, turns on a whole bunch of appliances, and increases their consumption from the grid. In the winter, this coincides with all of our solar access trailing off as the sun starts to set. In the summer, it's the hottest time of the day, often is the afternoon and evening. So all those air conditioners are cranking and everybody's trying to cool their house down. So what the utility will do is say, okay, let's say from, in this graph, it looks like from noon to 6, but a more common time frame is maybe 3 or 4 to 8 or 9 in the evening. We're going to have the highest rates of the day, meaning the kilowatt hour that you pay for that period of time might be as high as, 40, 50, maybe 60 cents a kilowatt hour. Whereas in off-peak hours overnight, you might be paying more like 10, 15, 20 cents a kilowatt hour. Pretty significant rate signal there for them to charge you more during a peak hour. Oftentimes you'll also see a mid-peak or part peak displayed here in green. These are going to be hours of the day where maybe it's not 40, 50, 60 cents, but it's definitely higher than the off-peak rate because they know that they need to generate more power and that they can charge you for it. So how does solar and battery fit into this? Well, solar is going to be self-consumed and the battery is going to give you the ability to discharge during those peak hours. So, you can avoid most of these green and early purple hours simply by having a solar array to self-consume the power so you're not importing at part peak or peak rate. And then if you have energy storage, you can program it to say, hey, I want to make sure that 3 to 8 window is covered as well. Even though my solar's started to sunset for the day, my battery can provide the kilowatt hours I need so I don't have to import them. Putting it all together, an integrated solar and storage solution looks a lot like this graph on the right, where typical usage patterns may have a bunch of activity in the morning, people going to work during the day, using less power, but they're generating all this PV because it's the middle of the day, the sun is high. By saving that storage for later, you are avoiding a high import rate for buying during peak hours, but you're also potentially avoiding a low export rate. We're starting to see utilities like in California with NEM 3.0, where they're devaluing the export rate. So you really have no incentive to send this solar in the middle of the day to the grid because it's so cheap. Whereas if you can save it and use it for later, great cost savings can be realized. All right, let's get into the talk about battery chemistry. So we're going to talk about lithium-ion and then a number of chemistries within that lithium-ion family. So when we're talking about lithium-ion, we're going to have lithium ions moving around in a battery, and they're going to be moving around in a number of different elements. For our battery, and here in green, lithium iron phosphate, we're going to highlight a bunch of reasons why it's safer compared to these purple columns, which generally all have cobalt in their battery chemistry. The first and foremost is thermal runaway and fire. Our batteries do not have the risk of thermal runaway with propagation that these other battery chemistries do. We also don't have toxic elements in our batteries. Now, no battery is truly landfill safe. They need to be recycled in the proper methods. But our battery is going to be much safer for the recycling centers if they don't have those toxic elements in them. So not only what do we do when we're done? How do we get those batteries out of the earth? How do we get those elements out of the earth? Are there abusive mining practices? Well, in our safety and standards talk last week, we talked about how cobalt extraction does involve some questionable practices that we are able to avoid because we're not extracting that element. Another consideration might be ventilation or cooling, neither of which are required for our battery. So if you're looking at that 9540 certificate, you're not going to see that we need to have additional cooling equipment or additional ventilation like you may see in some other chemistries or safety monitoring equipment. Don't need any of that. And we have a wider temperature range, and we'll see a slide on that shortly. So let's talk a little bit more about these chemistries. So on the left, we've got the various chemistries. I said they involve cobalt. They involve a lot of other things. All of them involve lithium. We've got nickel manganese, nickel aluminum. These chemistries all have their own place. The cobalt chemistry is generally much more energy dense and therefore can be much lighter. Applications for this may involve a drone, where a lithium iron phosphate battery may add unnecessary weight to the drone, making it not fly as long, not fly as well. So generally in mobile applications, a cobalt battery may be fine, may be actually preferable. But when we're talking about energy storage for our homes, our businesses, these are stationary batteries. So energy density is not as much of a concern. And for my home, I am definitely concerned about fire. And having a battery on the side of my house that has the propensity for thermal runaway with propagation is concerning. But chemistry isn't the only way that we differentiate ourselves. There's also form factors. So any of these chemistries could be in a cylindrical cell. Again, I compared it to a AA. Kind of looks more like a C battery in that picture, but you're used to them. You've seen them your whole life. They're a positive and a negative terminal on opposite ends of a cylinder. Within the cylinder, there are wrapped layers that are the cathode and anode and the separator that allow the battery to exchange electrons. This form factor is generally very sturdy. It offers reduced thermal expansion and contraction because of a metal case. And so therefore, it's generally much safer. The next one down is a pouch battery. Now, a pouch battery, you might find one of these in your phones, like I said, a drone. Now, these are going to be a great form factor for a lightweight product, a mobile application, maybe something that is on the go. Now, that pouch itself doesn't offer a lot of structure. Thermal expansion and contraction can occur. And over the course of the battery, that can lead to degradation, could lead to puncturing, could lead to one of those thermal runaway events. So we've chosen not to use the pouch factor in our battery. Another form factor is prismatic, and it's kind of a combination of the two in that it's a more rigid structure than the pouch. But like the pouch cell, you have positive and negative terminals right next to each other, increasing the opportunity to short if those terminals are contacted by a conductor. And there's still some thermal extraction and contraction that is going to happen in prismatic cells, again, leading to degradation, potentially even damage to the battery over time.
So I'll jump in here just for a second to talk about the form factors and the chemistries. As Chuck said, the chemistries here, there's a need for lightweight sometimes, and there's a need for more power density. But I think it bears noting that the major car manufacturers are actually switching over to LFP. And I often point out that in 2022, both Rivian and Tesla produced more than half their cars with LFP. So switching to the LFP, there's the reduced risk of fire. And so all of those cobalt-based chemistries, even the LMO batteries, typically have a small dopant level of cobalt in them. And that higher voltage makes them a little bit more likely to experience fires. In terms of the pouch cells and the prismatic cells and the cylindrical cells, the form factor, as Chuck mentioned, pouch cells are typically used in products such as Bluetooth headphones, things that you're not expecting to last for a long time. You might get 5 years out of a decent pouch cell, but as you mentioned, the expansion and contraction shortens the lifetime, and it also makes the battery much easier to puncture, etc. Similarly, on the prismatic cell, there's a benefit there that it's a lower cost to manufacture. These come in large packages, so you can get an individual prismatic cell that's a very large cell in terms of capacity, so that makes it less costly. But because of the form factor, there are a couple of downsides to it. The heat migration out of a large cell is slower. So typically the discharge rate and charge rate have to be a little bit slower. And that heat that can build up there results in expansion and contraction, as Chuck mentioned. And that expansion and contraction from prismatic cells typically makes their lifetimes a little bit less. So we're using the cylindrical cells in all of our batteries as a way for us to give the longest lifetime. So the expected lifetime of these sealed cylindrical cells, they're hermetically sealed, which means that no air goes in or out. They do have a vent on the top to prevent the risk of explosion, but that is sealed unless a high pressure is reached, typically around 10 atmospheres. So we use that cell to offer the longest lifetime to our customers. Don't get us wrong, there are reasons why you would use the pouch cells and prismatic cells as well. But we're using that cylindrical cell, and you can really think of the cylindrical cells as making kind of the top of the line batteries, but they come at a higher cost. So thanks, Chuck.
Yeah, thanks, Nathan. That was great. So there we have it. We're using the lithium iron phosphate chemistry with the cylindrical form factor for, like Nathan said, the top of the line in safety and lowest degradation over the lifetime. So what is thermal runaway? I've mentioned it a bunch, and we want to make sure that we cover the concept so that there's not misconceptions. Now, thermal runaway is when a battery gets hot enough, a chemical reaction begins, that generates heat, and then that further accelerates the reaction. That's the runaway part. So generally speaking, they'll cause off-gassing, fire, or an explosion. So when we're talking about a thermal runaway event, what causes it? Generally, it's a failure of some sort, like a short circuit. That could be caused by those terminals getting shorted. That could be caused by a puncture or damage or a car crash. Like Nathan said, some leading EV manufacturers are moving to lithium iron phosphate probably because they're catching a hard time for their batteries, catching fire in cars. People don't like that.
Yeah, so typically with a car crash, you have a lot of stress that can be placed on a battery pack, right? And so there's much more likelihood of having a fire based on that crash. So internal short circuits when cases are dented, etc. And don't take our word for it. Spend a little bit of time and just look up some puncture tests of different battery chemistries versus LFP. So there are some notable YouTube channels that show puncture tests of NMC and LFP side by side, and there's a major difference there in terms of the problems that arise from those kinds of short circuits. And of course, everybody knows this Galaxy Note 7, which was banned on flights about 7 or 8 years ago, as a notable example, kind of giving lithium batteries a bad name in terms of fire. So what Chuck's showing you there on the screen is he's got a cell pack there, and he's showing you a little diagram of how to think about a cell. If we get a little bit more sophisticated, the cell actually acts as a little bit of a capacitor as well, because you have a separation between positive and negative in the same way that a capacitor does. So it's slightly simplistic, but what we're talking about here is the likelihood of thermal runaway. So if one cell does get hot, does short circuit, right, what's going to happen? And I'll let Chuck finish that off. So Chuck, what does happen when a single cell for our LFP cells, when it gets too hot and goes into a short circuit condition, what happens?
Not a lot. So to Nathan's point, like if you look up puncture tests for different lithium ion batteries, some of them can look like a firecracker or worse. There's fire, there's explosion, there's off-gassing, deflagration, which is basically flying pieces. For a lithium iron phosphate battery, when you put it through that same puncture test, there's a little bit of some fizzle. You can see that it's been punctured and there's some off-gassing, but what's really not happening is the thermal event that starts to run away. And that's really the key takeaway here, because if we look at this diagram at the bottom where we've got a whole bunch of these cells, maybe only one of them receives the impact that causes a short circuit. And if that's isolated, it may not be a huge problem. But now if they continue to have a thermal runaway event, now this entire pack is going to be experiencing that same kind of energetic off-gassing fire, propulsion of pieces, and that could be catastrophic. So we'll look, the next slide looks a little bit at what happens, but it's also worth noting that it doesn't have to just be a puncture. There could be an external heat source. In fact, in the 9540 tests, 9540A test, that's what they do, is they wrap cells in heaters to get them to go into thermal runaway. So it could be an external heat source. It could be overcharging. You got to be really careful with your set points on batteries, because if you overcharge them, you can have thermal runaway. In fact, a lead acid battery can also have thermal runaway. If you continue to charge it, overcharge it, the resistance becomes less, the battery takes more and more, and now you've got a thermal event mixed with a acid-based electrolyte, all bad. So thermal runaway is definitely something the industry needs to keep an eye on, because like Samsung learned with that phone, it is not looked upon favorably. So let's talk about the numbers of thermal runaway. We've talked about what happens. There's going to be vaporizing of the electrolyte, causing some off-gassing. That gas is contained, great. But if it escapes, it's toxic and flammable. Now, lithium iron phosphate, or LFP, can reach a higher temperature than an NMC battery or other cobalt-based batteries before thermal runaway begins. So that's about a ballpark of about 200 degrees centigrade for LFP to reach thermal runaway. NMC might start as low as 170, so not as hot. What's more is that LFP batteries, when they do reach that thermal runaway, reach a lower maximum temperature than other cobalt-based chemistry. So, if you get that LFP battery at 200 degrees centigrade, thermal runaway starts, but it's going to max out at, say, about 400 degrees centigrade. Still very, very, very hot, but not as hot as a cobalt-based chemistry that's cooking up to 675 degrees centigrade. Further, an LFP battery is going to release less gas in these events. And I believe it's the next slide here, where we're going to look at how these gases contribute to the overall heat curve of a thermal runaway event. So less gas is obviously better. So this is a third-party graph by Sandia National Laboratories. In case nobody's asked it in the chat already, we will send out a copy of the slide deck. And so all of these hyperlinks to what we're talking about will be available for you. Like Nathan said, do your research, watch some puncture tests, be informed, because this is a really important topic in our industry. But what we're looking at here is a thermal runaway of different cell chemistries. So each cell chemistry is a different color. On the horizontal axis on the bottom here, we're talking temperature in degrees Celsius. And on the vertical axis here, we're talking about the normalized heating rate. So normalized meaning that not all batteries are the exact same size. There's different form factors, as we've been discussing. But even within a cylindrical cell, there will be different sizes. And so to treat them fairly, they are normalizing the heating, the energy being released in a thermal runaway event based on a degree per amp hour. So they're trying to keep the playing field even here.
Yeah, and I'd like to try to point out what's happening here. So if you imagine taking a battery cell and heating it up to force it into a thermal runaway, eventually the electrolyte, which is an organic gel that's inside between the cathode and anode layers, will get hot enough that that organic gel will turn into vapor, right? And when that vapor ignites, it will result in the cell temperature going up. And so what we're looking at here is how quickly that cell temperature goes up when we force the cells into thermal runaway. So that's what's happening here. And Chuck is going to talk to you about the performance of LFP versus these other chemistries. And this graph is really an illustration of how quickly, right, different cell chemistries can result in fires, rapid fires. So Chuck, what happens here?
Yeah, so all of these batteries are being exposed to the same temperature. The first one to really take off here is lithium cobalt oxide. And you can see the normalized heat skyrocketing right away at a very high rate, going to a very high normalized heating rate before calming back down. Similar with other cobalt chemistries. Here's NMC in red. And LFP appears to be flatlined down here. And in fact, we have to zoom in 100 times to even really visualize the LFP curve. And so, like we talked about in the last slide, it's a slightly higher temperature that needs to get the LFP battery to take off. As it does, to Nathan's point, that electrolyte starts to boil and off gas, creating a vapor that is flammable and increasing the overall heating event. But it really kind of caps off here pretty quickly, where we can hardly see the bump here. You can see it better here, and then it just drops off. And as other batteries are coming back down, in that higher temperature range, like we talked about in the last slide, LFP is relatively cool comparatively. So really, another way to think about this graph is the amount of energy these batteries are releasing. And when you talk about a thermal runaway event, the runaway is really that out of control energy release. Because you could bet that if you're a battery sitting right next to one of these real steep curves, it got really hot really quickly. And what does that mean for you as a battery? Now, are you also going into thermal runaway? Because that's thermal runaway with propagation, and it's not a good thing. Again, take the time, check out these slides, read the article. It is fascinating stuff. A lot of good YouTube videos out there on the subject as well. So because of this, there are different safety approaches. If you know that you don't want your battery getting hot enough to go into thermal runaway, because it's a problem for your cobalt-based chemistry, you can have some additional equipment. You could have ventilation, cooling, maybe thermal monitoring equipment that's connected to your system. But these are all added costs. These are all moving parts. So there are additional points of failure and can very well be a parasitic drain on your capacity. So, if you're trying to run a radiator that's pumping coolant through a battery, you're using up your battery's available energy to do so. So because Simplify batteries have a wider operating range than cobalt-based batteries, we don't need all this additional equipment. And because we don't have thermal runaway, there's a whole bunch of ancillary equipment that we don't have to include in our systems. And that reduces the levelized cost of energy, which we will go into here in a couple slides. But, it's important to note that we don't require ventilation, cooling, or thermal monitoring. That said, your AHJ may still require it. Even though our battery doesn't need it, they may still say, hey, we want heat sensors, or hey, we want a fire suppression system. And that's really because the industry has had batteries have events, and it's given the industry a bad name. But our batteries are inherently safer and don't require this equipment. So here's that operating range I've been talking about. Operating, let's call that discharging. So we can go as cold as -4 Fahrenheit up to 140 degrees Fahrenheit. You may see other cobalt-based chemistries topping out at maybe 120 degrees Fahrenheit for their operating temperature. So, if I'm in an area that could get up to, 110, 115 degrees in the summer, that battery is going to need a cooling system so that it doesn't go outside of its operating temperature, potentially during a public safety power shutoff event where I'm trying to get my house cool with my batteries because the utility turned the power off. Now, charging temp's a little bit different story. There's a problem with lithium-ion in general, not a brand-specific problem, but that the lithium ions don't like to be charged below freezing. And so you'll see, realistically, any lithium-ion batteries can tell you do not charge it below freezing. Now, there are some exceptions, and we'll go over that when we get to our Amplify product, where we have a smart BMS. But as a rule of thumb, charging a lithium-ion battery below freezing is bad for the battery. It can cause permanent damage and lose capacity. So because of this high, wide operating temperature, we don't need coolant, heating or air conditioning, or ventilation. There's another aspect of lithium iron phosphate that we at Simplify are very proud to offer an extremely long life cycle. We're going to warrant 10 years, unlimited cycles to 100% depth of discharge. Now, if you read other batteries warranties, there's a lot of fine print in there where they'll say, hey, you can take a battery down to 70% or 80% depth of discharge, but they may not want you taking it all the way to 100. Or conversely, if you do take it all the way to 100% depth of discharge, you may only get 70% of the nameplate capacity at the end of that 10-year warranty. Now, and I should have said at the top here, the numbers up top are state of charge. So 100% state of charge is 0% depth of discharge. It's a very common terminology in the industry, but we do allow you to cycle to 100% depth of discharge if you want to. Now, we recommend 80% depth of discharge because we know from experience, batteries that are still out there in the field, that if you're very kind to your battery and not going to 100% very often, your battery will outlive 10 years. And I believe we have a slide on that coming up here. One of the things that's really unique about our battery, and I love it, I've loved it since I first laid eyes on it, is that our battery has a breaker on it. Every single one of our batteries. This is a great safety feature. You can turn the battery off and now your terminals aren't hot. It's perfect for when you're wiring or when you're testing batteries. You're able to do a whole lot where you can isolate, a single battery or isolate part of a bank. In addition, all of our batteries have a BMS, which is a battery management system. So a BMS can serve many functions, but at a very high level, what a BMS is doing is providing some layer of overcurrent protection, meaning that you're not putting too many amps into the battery, too much power into the battery, or taking too much power or amperage out of the battery. Further, a BMS accomplishes cell balancing. So again, this battery is made up of a whole bunch of small battery cells that look like AA batteries or so. And in charging, they may not all charge exactly equally, but the BMS enables them to balance essentially during our absorb cycle to make sure that each of those cells is individually charged up all the way, resulting in a fuller charge for the battery as a whole. Now, there are also some built-in protections for short circuit protection and charge discharge protection in a BMS, but these do not substitute for a poorly designed system. You should never use a BMS as a backstop for not designing your system correctly. Your BMS should be there for when things go wrong. Your charge controller is putting in more amps than it should. That would be something where you'd hope the BMS would catch it, but you don't want to just let your charge controller go full bore, knowing that the battery can't take it and expect the BMS to be that backstop. When we talk about batteries, we talk about a C rate. Now, the C rate is the charge rate. So it's the rate at which a battery is discharged or charged relative to its maximum capacity. In the lead acid world, if you've been using, lead acid batteries for home energy storage, you may be seeing C5, maybe even C10 rates, meaning that battery can only really charge over the course of 5 in a C5 rate or 10 in a C10 rate hours, which is a really long time. A C1 rate means that entire battery could charge or discharge in 1 hour, which is very fast. Our batteries are a C/2, which means that you can charge the whole battery in 2 hours, or you can discharge the whole battery in 2 hours, which is pretty fast. And it's important to understand that this rate is relative and holds true for any size of the bank. So what that means is that a relatively small bank can provide significant power. As we'll show in a sizing example, discharging a battery at C/2 means that one of our 3.8 kilowatt hour batteries can provide 1.9 kilowatts of power. You start to stack those up, and a relatively small bank can be providing significant power. Another key feature about our batteries is scalability and expandability. When we're talking about scalability, we're talking about paralleling multiple batteries. So with our 5 battery, there is literally no limit to the number of batteries that you can put in parallel, resulting in increased energy storage. And as we start to stack up those 1.9 kW of power at the C2 rate, increased power availability. With a 5 battery, there's no communication lines to run. And like I said, you're scaling up both energy and power. We can also expand a bank. Now, our rule of thumb is, say, 2 to 3 years, depending on usage, that you can add batteries to a bank. After about 3 years, it starts to become maybe not so much of a good idea. But there are other battery chemistries that do not allow you to expand at all. Whatever you put in on day one is what you're stuck with. So a couple visual examples of that. We've got an airport hangar in Hawaii with 85 batteries. It's roughly 300 kilowatt hours. It's a lot of storage. Expandability, in this example, we've got a sunny island here. Started off with 8 5 batteries. And maybe the homeowner got some electrification going on, got an EV, got some different appliances. But they were able to come in after the fact and add 8 more batteries, increasing the gas tank. They didn't have to change out their combiner. They didn't have to change out their inverter. They have more energy. It's a key feature. Another key feature, if you're used to lead acid, is no maintenance. So like we've talked about, the LFP chemistry is very stable and self-contained. It's not venting, so you don't have to have venting systems. And you shouldn't really have to do any work on it over time. It also has a very low discharge rate of about 1% per month. That's with the breaker off and in storage. So we ship at about 30% state of charge. So, when you get your batteries fully charged up before connecting them to loads. But if you needed to store them for a year, go ahead and get them charged up to full, and they'll absolutely sit well for a year. You might want to continue to charge them maybe once a year or so, but at a 1% discharge rate, you can do the math. You've got a long time before they discharge themselves all the way. So big thing here is no maintenance. If you're used to a lead acid bank, you have all kinds of problems. You've got this acid electrolyte that you're having to water your batteries and check gravity on. In this photo, you've got all these white caps or different caps you have to remove to check the electrolyte and measure the gravity, and you've got temp sensors, and you've got all these nasty wires, and everything's covered in acid. It's a big mess. So this was a before, this is an after, where we took Simplify batteries and swapped them in for this lead acid bank replacement. Super clean, no maintenance. So real quick, we're getting low on time. We're going to run through our Simplify products. I've talked about it a bit already. Our 5 battery is the workhorse. It is a simple parallel connection, comes in 24, 48 volt options. There's an integrated BMS in there and a breaker. This is a great solution for a drop-in lead acid replacement like the last slide. More advanced, but same form factor, is our Amplify battery. This battery's got some closed-loop communication that is enabled with our Simplify ESS and the Solarc inverters. And this allows the battery to communicate to the inverter to tell it various things. Because of this, it can increase that maximum discharge up to 100 amps for 10 minutes. But it also has temperature protection. It can tell the inverter, based on its internal temperature, to throttle back charging at low temperatures. So this could be an exception where, due to a very slow charge rate, you might be able to continue charging below freezing because the BMS is communicating to your inverter. Likewise, it could tell the inverter it's getting too hot and it needs to stop discharging as much. Because of communications, you can parallel up to 75, which is still huge. And it makes commissioning easier because you've got some auto-populating set points. Now, there's still going to be what I call customer expectation set points, where you're going to go in and say, okay, how far are we discharging the battery, and when does my Jenny start? How does the system behave? But the battery is going to tell the inverter the set points that it needs to keep the battery happy. On a smaller scale, we've got a 12 and 24 volt Phi battery. These have the ABS case. They're great for a mobile application. Same chemistry, same BMS, same breaker. We've got some even more mobile stuff where we've got these expeditionary products, each coming in their own kind of little suitcase. One with some solar panels. They have a battery and inverter charger built in. So you could be charging this up for a camping trip or tailgate. If you need a little bit bigger one, here's a suitcase on wheels. And we've also got some express cabinets. Now, these are small. This might be like a good backup for like a apartment or something where you're not backing up, metered loads, but you need to back up a couple of sockets. I've also seen installers use this for MSP swap outs, where the homeowner's going to be without power for a 10-hour day while we're, waiting for the utility to come back and reconnect the MSP we just wired up. So you could be running lights in the fridge, maybe keep the TV on. Similar cabinets, but not mobile. We've got our access unit. So again, this has a built-in inverter charger. We have this with Schneider, Solar, and our new ESS is coming out soon. So you've got batteries in the bottom, inverter in the top, and you're going to get some 9540 UL listings on these products, which is becoming more and more important. Maybe you don't need an inverter, you just need storage. Our Boss 6, because it can fit 6 batteries, or our Boss 12, which fits 12 batteries, again, giving you that 9540 certification for the energy storage, outdoor rated, for a pad, mount it, and you're ready to go. We also have an entire high voltage team that are doing high voltage racks and containers for large energy solution projects. You could be doing megawatt hour jobs with these guys. So if you have any questions about the high voltage team, please let us know. We can put you in contact with them. And like I said at the top, we're super excited about our Simplify ESS. So this is a versatile, scalable, and simplified solution. We've got our own battery, we've got our own inverter, and you can do all the things we've been talking about as far as scalability while also stacking inverters. So it's a 6K inverter and a 4.9 kilowatt hour battery. This is going to come into play with jurisdictions that are limiting kilowatt hour storage to 20 hours. So if you have 4.9 kilowatt hours, you're staying below that 20 kilowatt hour ceiling. Very important. Also has its own monitoring for installers and homeowners through our Energy Track control system and app. 6K inverter can stack up to 9 in parallel. It's got a seamless transition, and it's got a screen. You gotta love that it's got a screen, because oftentimes when people are in an outage, what else have they lost in addition to power? They've lost internet. So that app might not be working for them, but the screen will. Outdoor rated, 10-year warranty. So the 10-year warranty is coming from a single company, single tech support call, battery, inverter, and monitoring. 4.9 kilowatt hour battery, scalable up to 358.5 kilowatt hours. So you could do a pretty sizable bank here. Same features we've been talking about all day: lithium iron phosphate chemistry, built-in breaker. This has the amplifies closed loop communication system, so it can tell the inverter what it needs. Outdoor rated, 10-year warranty. And the app. So it's really important for homeowners these days to have a way to monitor their system, whether they're home or away. The Energy Track app offers that for the end user. It also offers it for the installer and for the fleet. So you can have your entire fleet available to be monitored in an app. Your installer can be commissioning with the app, and your homeowners monitoring their system as well. Real quick, I want to talk about levelized cost of energy, because not all systems cost the same. Now, when we talk about the cost of a kilowatt hour, we really want to talk about the cost of that kilowatt hour in the life of the system, because the similar lead acid bank might have a nameplate of a similar kilowatt hour, But if you're only taking it to 50% depth of discharge, you don't have the same usable energy. Further, over time, as that battery degrades, you're not going to get as many kilowatt hours out of it. So it's very important, if you're selling to the end user or if you're creating the cost analysis, to understand that the levelized cost of energy of a lithium-ion system will be lower than a comparable system that maybe has a lower upfront price tag, but it's going to have costs associated with maintenance, with replacing the system, with ancillary costs like fire suppression and heat sensors. So we have an entire calculator to do this equation for you. If you just click here, you can go in and say, hey, I've got 12 L16 batteries, and it's costing me this much, but I need to do a replacement at 5 years, and I got to build a battery box for venting and build in all of those costs. And then you compare that to a similar sized Simplify bank that doesn't have to be replaced at year 5. And you're going to find that the levelized cost of energy is actually lower, again, despite that higher upfront price tag. It's a very important concept for your end users to understand as well. Real quick on battery sizing, we talked about depth of discharge. We anticipate if you go to 80% depth of discharge, you're going to get 10,000 cycles out of our battery. You can do 100%, but you're really only going to get that 10-year warranty life, where 10,000 cycles pencils out to something more like 20 plus years. Depending on the application, you might say, hey, if I got a battery backup system that's only going into backup maybe a dozen times a year, 90% is appropriate. But if you're off grid, or if you're cycling to the grid daily, you're using that battery 100% or to 80% daily, we're going to say 80% is a good number, because you're going to get that maximum life, get those additional years after warranty. When we're sizing our battery, we want to keep that C2 rate in mind. So in this example, we've got an Outback 8048, which is a 8,000 watt inverter. So if we know that our 3.8 kilowatt hour battery can be discharged at a C2 rate, we know that a single battery can do 1.9 kW. Now, if this inverter can pull 8 kW from our battery bank, we're going to need 5 batteries minimum to be able to provide the power that this inverter can pull. If you undersize the bank and the inverter pulls the whole 8K, you're very likely to damage the batteries and to void the warranty. So sizing to a C2 rate is absolutely imperative at the system design phase. Moving real quick here, we've got a bunch of links. Again, you'll get the slide deck, talk about sizing, replacing lead acid with a Phi battery, and levelized cost of energy. A couple notes on installation. Always read the manual, please. We've also got spec sheets at this link called product documentation, but the real kicker is the integration guides. These are going to give you step-by-step programming for various pieces of equipment that we've integrated with. So if you're doing an Outback system and you need to know all your set points, print that document out or download it to your phone, so when you're out on site programming it, you have what you need. Mounting, super simple, like we've gone over with all the fire safety. We don't have a bunch of ancillary equipment. Really, don't mount them upside down. That's going to be the big takeaway. You can put them on their side, you can mount them right side up, but don't mount them upside down. We don't want that weight of the battery resting on the innards. Parallel wiring. So in this example, you can see that we've got equal length battery cables. This guy has to snake around a little bit because he's got so much battery cable. We want to have all of our batteries wired in parallel, never in series. To do that, you might have to go to a DC combiner, where all of your parallel leads are landing on these large DC buses, and then your inverter out for positive and negative are some nice big fat battery cables going to the inverter. Again, wiring in parallel. And always use a torque wrench. Don't hit our batteries with an impact driver. You can snap the terminals right off. 160 inch-pounds is probably not as tight as you would expect. So a torque wrench is going to get you to where you need. Again, take care of the batteries, they'll take care of you. Couple of system examples here. This is a DC coupled system with a solar arc and some rapid shutdown on the roof. We got a couple Boss cabinets wiring into one of those combiners from the previous slide. This is grid tied with a backed up load center. You can do the same thing with AC coupling, provided your inverter charger can handle it. Got micros on the roof here. You can also charge from a generator with our ESS. I did not mention that, and since we were acquired by Briggs & Stratton, it's an important concept. If you've got a home standby generator, you don't want that thing running all the time. So why not have it run, charge up a battery bank, and then use that battery bank to supply your loads? Real quickly on our Elite IQ installer program. This program is a way for installers who are installing our product to get on our map. We'll put you on here where people can search by their zip code and find qualified installers. We also have a cashback rebate, $25 per battery. So if you're installing a bank of batteries, you can put some money back in your pocket by doing the warranty registration and getting that rebate. If you're interested, please let us know. We've also got a photo contest where, we love photos of our systems when they look amazing. We love seeing our customers and their pets. So please, if you're an Elite IQ installer, send us some photos, get you in our photo contest with rolling entries. So if you didn't win in September, we still got your photo and you could still win. QR code, if you want to scan, it's just going to take you to this link that you'll get in the slide deck later today. And I also want to mention the Power Academy. Part of the Briggs & Stratton acquisition is that we've got some amazing resources at our hands, including an online instructional platform. We're moving more and more resources into that. Stay tuned because you'll be able to enter our IQ program through that soon and, brush up on battery and generator knowledge. And we made it a couple minutes over. If you were here for the NABCEP credits, thank you for coming. But please do send us an email so we know to provide you those credits. Tell us how you'd like your name listed too. If you're Robert, but your email says Bob and NABCEP knows you as Robert, it's important to get that right. So email us at training@simplifypower.com and we can get you those NABCEP credits before the end of the week here. Nathan, it looks like the Q&A is all about temperatures. So
yeah, it looks like Justin and Herman were so close here on the temperatures that I think we're going to give it to both of them.
Great.
So Justin and Herman, if you'll send us an email to training@simplifypower.com with your address, we'll get some swag shipped out to you.
Right on. Well, thank you everybody for attending today. If you have any questions, email us at training@simplifypower.com. And I hope you have a wonderful day.